simulated counterpart, you square the difference and you sum them. Why squared? There is a precise reason why they squared it. And at the beginning of my activity, I tried to, as a researcher, I said, wow, the square is something that is problematic. I will explain you in a minute why it's problematic. And they said, why don't simply take the summation of the difference without squaring? And I got a simulation that was completely wrong. And the reason is that negative and positive error compensated. So if you have a simulation that gives, on the one hand, very relevant positive errors that are followed by very relevant negative errors, they compensate. You get a sum that is zero, like, oh, my error is zero, sum of error is zero, but it's zero because there are very high positive errors that are compensated by very high negative errors, which is not good. If you square, of course, the sign becomes the same, and this is perfect. So this square was introduced in order to avoid compensation between negative and positive errors. It was also introduced because people tried to get to the top of this relevant question, to reply to this relevant question, what is a good objective function, people also tried to use statistical reasoning. So they tried to find an analytical proof of the fact that an objective function works well. And the analytical proof was searched for by using statistics. And therefore, what is a basic requirement for such objective function working well? A basic requirement, they thought, was that with increasing length of observed data, the estimation carried out by using this objective function converges to the true value of the parameters. So they thought, okay, the procedure may not work well with few data, because you understand that if the number of data that you have available is very small, if capital N is very small, you understand that it may not work well. While if capital N increases, you understand that it should work better. And therefore, they tried to prove that with increasing capital N, the objective function was leading to the true parameter values. This is something that you can also prove with your PC. If you get a problem for which you have a very long observed time series, you can see what happens if you increase the number of capital N by first trying to calibrate the model by using few data and then increasing the number of data. And you hope that by increasing, you converge to the final true value of the parameter. This is called in statistics consistency. Consistency means that you converge with increasing capital N to the true value of parameters. This is explained in my web pages. There is a link here, consistency. Let's click on it. And you see what is a consistent estimator. And it is proved, the consistency, with convergence in probability. In probability because, of course, you have to analyze the outcome of several trials, and the best way to do that is through probability theory. But we don't need to go in detail into this. I just want you to remember what consistency is. It means that if you increase the number of your data set, you converge to the true value of parameters. And there is another useful requirement, which is unbiasedness of an estimator. So we say that an estimator is unbiased. We say that an estimator means the procedure that we used, and therefore it means the least square objective function, for instance. We say that the least square is consistent, and indeed it can be proved that it's consistent. It can be proved. And this is why it was also adopted widely. There are assumptions conditioning consistency, but under these assumptions, it can be proved that indeed least square is consistent. And there is a second requirement. We want an estimator to be unbiased. What does this mean? It means that if we make several trials to estimate model parameters by using different subset of observed data. In this case, I'm using an hydrograph. I could find another one, and then a third one, a fourth one. So if I make several trials, and I get the average of the results, so I compute the average, the mean value, it converges through the true value. So I make one trial, I get one value. Okay, a second hydrograph, a second trial, a second value. I compute the average, which is the average between two numbers. And then I take a third hydrograph, a fourth one, I increase the number of trials. My expectation is that by this, the average of all the trials for increasing number of trials converges to the true value, which is in a way similar to consistency, but it's a different story. If you think on how I defined it, you see that it's different. In fact, an estimator can be consistent, but not unbiased. And it can be proved that least square, under certain assumption, is, again, unbiased, which is something that we, again, appreciate. So this is to give you an historical perspective and to give you a first objective function that you need to remember, and I may ask it at the exam. There are some problems with the use of the least squares. And what are these problems? It's important that we understand, because now we are introducing additional objective functions, and the reason is that we need to overcome some problems. So I told you that least squares is consistent and unbiased, but under certain assumptions. Fine. The problem is that these assumptions are often not met when dealing with hydrological data. And in particular, I try to explain what I mean with technical reasoning. What happens if you square an error? And in particular, what happens, look at an hydrograph. What happens if you square the error in the simulation of an hydrograph? The hydrograph has a relevant behavior. There is a lot of difference between low values and high values. This typically happens in rivers. In any river. There are rivers where this difference is more relevant. There are others where the difference is less relevant, but typically, if you think at the Po River, for instance, the average is 1500 cubic meters per second. The peak flow, which happens on average on 100 years, is like 14,000. So there is an order of magnitude of 10 between average flow and peak flow. If you look at the low flow, typical low flow, minimum flow in the which may occur every 100 years, it's something like 300 cubic meters per second. Compared with the high flow, 14,000, it means that it's about an order of 50 times. It's a relevant difference. What is the implication of this? The implication is that the error that you make in the simulation of the low flow is much lower than the error that you make in the simulation of the high flow. So if you have to simulate a low flow that is 300 cubic meters per second, at most your error is of the order of magnitude of 300. At most. It's difficult, so the order of magnitude I mean. If you simulate the peak flow, it's very easy that you make an error of 2000, like instead of 14 we simulate 12,000, and still we are quite happy because it's not a relevant error, it's like 10% less. But it's 2000. So you see that even in the error there is a relevant difference, order of magnitude of 10. If you square the error, like least squares does, you see that the difference is much higher. So 300 square, it's about 100 order of magnitude less than 2000 square, which is, which is relevant for its implication. Why is that? Because it means that you need to sum like 100 errors in low flows to get only one error in high flows. So what is the result? The result is that least squares give much more weight, about 100 times larger, to the simulation of high flows. And I said 100 for this simple case of the Po River. If you take like a torrent, the weight is higher of like 10,000 times. So least squares gives much more weight to the simulation of the high flows. So it's biased, the estimator is biased. You easily understand why. And so you may ask me, why did you say just 10 minutes ago that it's unbiased and now you're saying that it's biased? Because the assumption, the underlying assumptions are not met and we are not discussing them. I'm not interested. I just want you to notice that what the theory suggests doesn't match what the technical consideration suggests, and the reason is that the theory is conditioned by some assumptions that in the technical applications are not met, which is quite normal, no problem in that. But we have to take into account that if you are interested in the simulation of the high flows, because we are interested in flood forecasting, in predicting what order of magnitude an high flow may be, then least squares is fine. If you are interested in water resources management, and therefore typically in the low flows, least squares is not fine. So we have to find an alternative. For the low flows, before I move forward, let me introduce a transformation of the least square objective function. It has the same properties. It's just a transformation which is widely used in hydrology, widely used. And the reason why it's widely used is that it is rescaled so that the maximum value is 1. The maximum value of the objective function, which corresponds to the optimum, is 1. So how is least squares rescaled to get this new objective function? Okay, let's see. Look at least squares here. So I get it back. I write it here. Summation from, keep in mind that I'm writing in the center of the blackboard because I need also to write something here and something here. So don't put what I'm writing on the left margin of your sheet, okay? Just in the middle, okay? So I rewrite this. Summation time equal 1 to n of qt minus q hat t squared. Okay, this is divided by a denominator. The denominator is fixed for varying values of the parameters, and the denominator is summation time equal 1 to n of qt minus me qt okay, third parenthesis squared. instead of getting the difference squared and summed of observation minus simulation, I take at the denominator the difference between observation minus the average of all my observed data. Good. And I had a 1 minus here, and I call this E theta. I hope that I called E even here. Let me see. No, it's always F, so let me call it F again. This is called Nash-Sutcliffe efficiency. I just want to point out to you a curiosity. This objective function was introduced by Nash and Sutcliffe, and Sutcliffe is still alive, and Nash is already gone because he was older and older. It was introduced with a paper that was published in 1970. And this is the most cited paper in hydrology. Most cited, you know, that papers, scientific papers, their value is measured, among the others, criteria by counting the citations. Citations are when you get another scientific paper making reference to one paper, we say that the other scientific paper is citing the previous paper. So basically, it means that subsequent research is carried out by referring to a previous publication, which means that it gives credit to the previous publication, it gives value. This is criticized by some because, you know, one may cite a previous paper to say that it was wrong, so it's not giving credit. It's saying that it's wrong, but it is counted as a citation. But anyway, it's a reasonable indicator of the value of a publication. So basically, sometimes when we want to say, oh, my paper was very good, we say my paper was cited 100 times, which is already a good number. So the most cited paper in hydrology is Nash-Sutcliffe, and what they did in that paper, they just introduced this objective function, which is basically, on the one hand, it says that indeed calibration is a relevant issue in water resources management and hydrology. Second, it means also that not necessarily, I mean, this is something that it's not a real discovery. It's just a mathematical transformation of the least squares, and still it is the highly cited paper, the most cited paper in hydrology. So it's something that it gives the opportunity to make some interesting discussion. Anyway, let me technically clarify what this objective function means. First of all, let's look at the denominator. What is the denominator? The denominator represents, as I said, the square difference between each observation and the mean. And what does it mean if the sum of the model errors is equivalent, the same value with respect to the sum of the model of the observation deviations from the mean? It means that the predictive capability of the model is the same than computing the average. So if the magnitude of the model errors is equivalent to the magnitude of the deviation of the numbers of the observed data from their average, it means that the model is very poor. You understand why? Because if I don't apply any model, one just gives to me a series of numbers and asks me what is your guess on the next value, and you don't have any model, you don't know anything, what is the most trivial thing that you can do? It's compute the average and say the most likely value is the average. The most likely next value is the average. This is very trivial. So, of course, we make a mistake in doing that. And if the mistake that we make by just guessing through the average is equivalent to the mistake made by the model, it means that the model is poor. The predictive capability of the model is equivalent to the trivial prediction that we may obtain by just guessing with the average. Okay, so if this ratio becomes equivalent to 1, we are not very happy. We are happy if the sum of the model errors is 0. So we are happy if this quantity here becomes 0. We are extremely happy. If it is equal to 1, we are not happy. If it becomes higher than 1, it means that the model is even wronger than the average, which is something that we have definitely to reject. So, if we look at the value of this objective function is 1 minus this ratio here, I said that I am extremely happy if the ratio is 0, which means that my objective function is optimal with a value of 1. 1 minus 0 is 1. If the efficiency is 1, perfect. It means that the model is perfect. If the efficiency becomes 0, because the ratio becomes 1, 1 minus 1 is 0, it means that we are not happy, absolutely. If it becomes negative, because the model is even wronger than the average, then negative efficiency means something that we really have to discard. What is the advantage of this objective function? That basically it varies between 0 and 1. It can allow comparison with the model working in different conditions, different catchments, etc. While least squares, it's a number that doesn't give any information to you. You just try to minimize it. So basically, keep in mind that least squares, you need to minimize it, because it means minimizing the error. Efficiency, you have to maximize it, because maximizing means getting close to 1. In hydrology, there is a rule of thumb which says that a rainfall runoff model is good if efficiency is greater than 0.5. This is just a rule of thumb that I want to give to you just as a reference. And there is another rule of thumb which says that an efficiency, a very good efficiency, is 0.85. So when you apply hydrological models, you have to expect efficiencies between 0.5 and 0.9. And let me say that 0.5 is still very poor. I mean, I changed my rule of thumb is at least 0.65, 0.65. But of course it depends. It depends on the catchment, it depends on the available data, etc. Okay, but this is just a rescaling of the least squares. Now let's try to overcome the problem of least squares. The problem is, I just remind you that with the low flows it's less efficient. So there is a very trivial change to least squares that we can make in order to give more weight to the low flows. And the trivial change is just to remove the square. And in order to avoid compensation, taking the absolute error. So my f theta may simply be sum t equal 1 to n of qt minus q at t absolute value. That's it. If you don't compute the square, of course, you give less weight to the high flows. Another one, in order to give even more weight to the low flows, f theta is equal to summation t equal 1 to n of, again, absolute deviation, qt minus q hat t, divided by qt. The first one is called sum of the absolute errors. The second one is called sum of the absolute relative errors. There is one thing you should be careful of with the last one. If you divide here by the observation, of course you give more weight to the low flows because you see that this ratio increases for decreasing QT, which is a way of giving, of course, more weight to the low flows because it means that for increasing QT, high flows, you decrease the weight of error. But there is one potential problem here. If QT tends to 0, which may happen in a river, the individual error in the simulation of this observation goes to infinity. And therefore, this is something that you have to avoid. So you can't use this objective function with the intermittent flows, because if you divide by 0, you get an error. But also, if you divide by 0.001, it's not a desirable option. So this kind of objective function should be used only when the lowest flow is well above 0. You have to be careful, because it could be unstable. Okay, let me see if I'm missing something. I'm just stopping here with our review of objective functions. The literature proposed several other options. And in particular, there are options that basically work with yes-no, a sum of yes-no judgments over each individual observation, meaning that instead of getting the error, the difference between model and simulation as an indicator, people prefer to use a binomial evaluation of each observation, like this simulation is fine, the other one is not. And if it is fine, they give a score of 1. If it is not fine, they give a score of 0. This is interesting because it allows you to judge whether a simulation, an individual simulation of an individual observation is fine or not. With the computation of error, you are not allowed to make this difference. It may be a good option if, for instance, you are not interested in the simulation during a certain period, and therefore you give a value of 1 to all the simulation during that period, like during the winter. If I'm not interested in the simulation during the winter, I just focus on the summer, and to the simulation during the winter, I just give a score of 1 to each of them. And during summer, I may give the score of 1 only to the simulation of low flows, for instance. And so I forget about the high flows. And these are interesting options which we don't discuss in detail. I just want to tell you that, of course, the set of objective functions that you may use is not limited to these 4 options. Now, we were talking here about automatic calibration. Now, let's discuss about expert knowledge. When it is expert knowledge, calibration without using data required, it is required when you don't have data at all, or you have only a very reduced set of observed data. In this case, you can't use an objective function, and you may go through expert knowledge. There is not much to say about expert knowledge. Basically, you know how a model works, you know how the process works, and you guess the optimal value of parameters. For instance, you may refer to a catchment that is very similar to the one that you are considering. So you apply IMOD and you say, oh, this catchment is similar to the other one for which I know the parameters value, the parameter values. Let's adopt the same parameter values for this catchment where I don't have any observation. This is fine. Expert knowledge could be this, or could be for the linear reservoir. You may remember that I told you that the value of K is very close to the value of the time of concentration. So in absence of data, you may say, okay, let's guess the time of concentration of this catchment, and there are empirical formulas for computing it. And once that you guess the time of concentration, you may adopt a value for K that is the same as the estimated time of concentration. This is expert knowledge. There are several occasions, several cases where estimation through expert knowledge is needed. And this is why, as I said, you have to try to establish a connection between model and reality. You have to try to understand how the model works, how the reality works, and through this knowledge you gain your expert knowledge. As I said, there is not much to say. And there are several examples presented by the literature where they suggest how to base your expert knowledge. So they say, for instance, look at the land cover, look at the storage that the catchment may have. So if you get a guess of the storage, you equate your guess with the parameter Cmax of, for instance, of IMOD. And it helps a lot if the model parameters have a physical meaning. Like in the case of the linear reservoir, if we think that K is close to the time of concentration, we assign a physical meaning to K. K equivalent to time of concentration, physical meaning. Catchment storage, Cmax in IMOD, it has a physical meaning. Perfect. If we are able to assign a physical meaning to parameters, it becomes easier. That is to say that sometimes this physical correspondence is subjected to a lot of uncertainty. In general, you understand that expert knowledge entails higher uncertainty with respect to the use of trial and error or automatic calibration. Okay. Now, talking about uncertainty, which is always present, as we know, and in particular when we use expert knowledge, how to reduce uncertainty, or at least how to estimate it. So we calibrate a model, and then the client may ask us, but what is your faith into this model? What is your confidence into this model? And therefore we need, in a way, to prove that the model works reasonably well, or we have to provide an estimate of uncertainty, which is the same thing. So how can we test a model then? This is my next question. Okay, the model is calibrated, how can we test it? The way to test a model is called validation. It is also called in other scientific disciplines verification. Model testing, we call it in otherology typically validation. So how can we validate a model? Model validation. Okay. So let's suppose that we have a long hydrograph, a long observed hydrograph Of course, we always don't have it, but let's suppose that we have it for this time, and it's a long one. Like for the Poriver, you may remember that we have 90 years of daily data available. Okay, let's suppose that we are in a similar situation. And then we realized by intuition that these observed data may provide opportunities to test the model. So what could be our idea? The idea could be that if the observed ideograph is very long, we split it into parts. And so, with the same length, for instance, this is the part reserved for calibration. And then we have some left observed data that we can use for validation. So basically, by using our optimal calibration, in whatever way we got it, we simulate the first part of the ideograph, and we get something, a dashed line here. But we don't stop here. This is the part of the data that we use to get the parameters for the simulation. Let's continue the simulation with the new data. And what we see is that the dashed line continues, and typically we get more relevant errors. This is not very clear, but I wanted to write on the blackboard a dashed line that is closer to the data in the calibration